In 20 through 38, determine whether the statement is true or false. Justify your answer with a proof or a counterexample as appropriate. In each case, use only the definitions of the terms and the assumptions listed on page 161, not any previously established properties. The negative of any odd integer is odd. Well, by observation, this statement is true. 5 is an odd integer, which means -5 is an odd integer. That's true. 11 is an odd integer, and -11 is an odd integer. The statement seems to be true, so let's try to prove that it's true. Since we're proving a universally quantified statement, we're going to instantiate a fixed but arbitrary instance of an odd integer. So let n be an odd integer. And the goal is to show that -n, which is the negative of this odd integer, is also odd. So to do that, we're going to first unpack this assumption. What does it mean to be an odd integer? Well, according to the definition, this means that n equals 2k plus 1 for some integer k. Well, this means that -n is -2k plus 1, and that's by substitution. Substitution is one of the assumptions listed on page 161. So that means -n equals -2k plus 1, which we can simplify using algebra to be -2k minus 1. So this right here is -n. Our goal is to show that this -2k minus 1 is an odd integer. Notice that -2k minus 1, now to show that -2k minus 1 is an integer, now to show that -2k minus 1 is an odd integer, we need to rewrite -2k minus 1 as 2 times some integer plus 1. So I can rewrite this as 2 times -k minus 1 plus 1, again by algebra. Now, why would I rewrite this expression as 2 times some integer plus 1? Well, that's because the definition of an odd integer requires that the integer be written as 2 times some integer plus 1. If you distribute this 2, we have -2k minus 2 plus 1, which is minus 1. Now, since integers are closed under multiplication and subtraction, then -k minus 1 equals m for some integer m. That's one of the assumptions listed on page 161. Now we can summarize our findings. This integer -n is equal to 2 times m plus 1 for some integer m. That means by definition of an odd integer, -n is an odd integer. So now we can finish with our conclusion. Since we've proven that -n is an odd integer, that means the negative of any odd integer is odd. And just to remind you why we can say any odd integer, even though we've only proven this statement for some fixed arbitrary n, not every single one, is because of the arbitrariness. It doesn't matter what the odd integer is, replace n with that odd integer, and this proof demonstrates that the negative of this odd integer is also odd. And that's the proof of this statement. Thanks, everyone, and I'll see you in the next video.